Hello friends, it's a good afternoon here. I hope it's a beautiful afternoon wherever you are. Today I welcome you back to this episode of Learning Physics with IBM, and today I want us to continue from where we stopped with thermal properties. We said we shall be actually studying under thermal properties. We shall be studying ideal gases. We shall be studying temperature as a unit, and we shall see thermodynamics. So I would like to inform you that from part one and part two that we have already seen, it means ideal gases is covered. A more detailed examples or worked past paper questions will be seen later on at the end of the unit after we are done with the temperature and thermodynamics. We shall run through the past paper questions so that we can actually gain confidence in dealing with this unit. This unit is simple, but later on we will see when you study temperature, you will see that actually it reaches a point where some concepts appear to be quite abstract. But I know you will bear, and you will always tell yourself that actually this is A level. So you have to do whatever it takes to master the concepts and to apply them in answering most of the questions. So today we are done with ideal gases, and I want us to first skip temperature because many concepts of ideal gases are actually linking us to thermodynamics or are actually requiring concepts under thermodynamics. So we shall go straight to thermodynamics. We shall go straight to thermodynamics today. So under thermodynamics, we shall be so much interested in two major concepts. That is the concept of internal energy and the so-called first law of thermodynamics. Actually, if you're a chemistry student, you realize that there could be three laws of thermodynamics. For us, we shall only concentrate on the first law. I think there is a second law which states that actually heat naturally flows from regions of high temperature to regions of low temperature. That is considered to be the second law of thermodynamics. The second law of thermodynamics, I think that is the second law of thermodynamics. Heat naturally flows from region of high temperature to region of low temperature, even if there is no work done. But then if heat is to flow from regions of low temperature to regions of high temperature, then external work must be done on the system. This is an example of a refrigerator. For example, a refrigerator absorbs heat at room temperature inside and expels it behind it where the temperature is totally high. Things like a heat pump or how they call it, is it an air conditioner? It absorbs heat at relatively low temperature, but again it expels it in an area or in a region where temperature is very high. Naturally, a device cannot do that unless external work is done. That's why in a refrigerator, there could be something pumping a liquid throughout the refrigerator, and therefore external work is done. In an AC, there is a motor which does actually work. So, but naturally, without any work, you can put an object there, or you can heat one end of a metal and the other end also become warm because heat naturally flows from a region of high temperature to a region of low temperature. If we want it to flow from a region of low temperature to a region of high temperature, then external work must be done. So that is considered to be the second law of thermodynamics. Of course, there is the third law, which I think says chemistry students will now love it, and I think they talk about entropy. I think the total entropy is always increasing. The total entropy is increasing. I think that is the third law of thermodynamics, but for us, we shall not talk about the third law of thermodynamics. So we shall concentrate on the first law of thermodynamics. So to begin with, let us start with maybe internal energy. Let's start with internal energy of a substance. I think earlier on we have seen from IGCSE that substances exist in the three states of matter, that is, solids, liquids, and gases. We characterized these three states by looking at either the arrangement of the molecules or the movement of these molecules or the force of attraction between these molecules. That's how we were able to characterize these three states or three phases of matter. We mentioned from IGCSE that solids, for example, they have a specific property which we call rigidity, that their molecules are arranged in a regular pattern called lattice. The molecules or atoms are tightly bound together by a strong interatomic force. Therefore, solids have their atoms fixed in vibrating about fixed points. So we said for solids, the atoms move, but their motion is restricted about fixed positions or about the same position by just vibration. We mentioned that there exist relatively smaller spaces between atoms or molecules of liquids. So liquids are relatively, their atoms or molecules are relatively far from each other. So molecules can slide past each other. That's why when you pour a liquid on a table, it spreads on a table because the molecules can easily slide past each other. The force of attraction between the molecules is relatively weaker. That's why they are able to slide past each other. In gases, we said that the molecules of the gases are far away from each other, that the force of attraction between these molecules or even the force of repulsion between the molecules is relatively weaker. These molecules are free to move about each other at a very high constant speed. So the molecules of gases are free to move. These were the three states of matter. So the most important things we're mentioning here are the force between the molecules and two, their relative motion. So we can therefore characterize these three states of matter by reconsidering their arrangement and order or even the motion of their molecules. In fact, we could have equally said that the three states of matter have their molecules with different amounts of either kinetic or potential energies. So, when we talk about internal energy, we must be referring to two important things as long as we are looking at internal energy of a system. Because a system is either a solid, a liquid, or a gas, and this system is made up of either atoms or molecules. These atoms could be having both kinetic energy and potential energy. So somehow the internal energy of a system is related to these two things, the kinetic energy of the molecules which make up the system and the potential energy of the molecules that make up the system. You might be asking yourself what contributes the potential energy and what contributes the kinetic energy. So when we talk about the internal energy of a system, we are actually referring to the kinetic energy of all the molecules that make up the system and the potential energy of all the molecules that make up the system. So liquids and gases are going to be characterized in the arrangement, order, or motion of their molecules, as we have already seen. And we could equally have said that in the three states or in the three phases, the molecules have actually different kinetic and potential energies. Of course, kinetic is associated with motion, but then the question would be, how about potential energy? We wrongly define potential energy as energy possessed by a body at rest. I think that is now for an IGCSE student. An object could still have potential energy even when it is not at rest. But of course, when it is in motion, it has both potential energy and kinetic energy. So, the kinetic energies of the molecules in any of those three states, either liquids, solids, or gases, together with the potential energies of all these molecules, contribute to what we call the internal energy of the system. The potential energy and the kinetic energy of all the particles that make up the system contribute to what we call the internal energy of a system. So how shall we precisely define internal energy? Note that we said, according to Brownian motion, it proved that the particles of liquids and gases were in continuous random motion. This is why we saw the pollen grains, according to Robert Brown, moving in a zigzag fashion or in a random motion, because they were always continuously bombarded with, or they were always continuously colliding with the water molecules, which are moving in different directions, keep changing the direction of these pollen grains. We saw that we could extrapolate Brownian motion by observing smoke particles. We saw that tiny soot particles, those black particles in smoke, were observed to be moving in a zigzag fashion when illuminated with light. I gave you an example yesterday that you can view dusty particles through a ventilator very early in the morning when the sun has just risen. You will see that the dusty particles are moving in a funny fashion, simply because the dusty particles are continuously colliding with the air molecules, and we call this Brownian motion. But we said it doesn't imply that solids molecules are permanently at rest simply because they are tightly fixed together. We said for solids, the molecules as all the atoms are also in continuous random motion, but their motion is restricted to vibration above the same point. So for all matter, the particles are in continuous random motion. So in defining internal energy of a system, the term random motion is very, very important. So these particles are in continuous random motion. Therefore, we shall define internal energy as the sum of the random distribution of the kinetic and the potential energies of all the molecules which make up the system. So when I talk about internal energy, many times you'll use letter U for internal energy, or sometimes delta U for internal energy. I am actually referring to the sum of the kinetic energy plus the potential energies of all the molecules which make up the system in their random motion. That's why we say it's the sum of the random distribution. The word random is extremely important. Random distribution of the kinetic. It is the sum. That's why I've put an addition sign here. The sum of the random distribution of the kinetic and the potential energies of all the molecules which make up that system. That's what we are going to call the internal energy of a system. It's the sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. So this is the simple definition of internal energy. So we can simplify the internal energy of a system by adding up the kinetic energy and the potential energies of all the molecules which are making up that system. That's why we have defined internal energy as the sum. The word sum is extremely important because we add up the kinetic energies and the potential energies of all the molecules that make up the system. The word random has been highlighted because these molecules are in continuous random motion. Although for solids, the random motion is restricted to vibration above the equilibrium position. So this is what we are going to call the internal energy of a system. So for every system, look at the sum of all the kinetic energies of all the molecules and the potential energies of all the molecules. Then the sum of those two will be the internal energy of such a system. I think we saw something similar to this under work, energy, and power in AS, but I must have said that this will be seen in details at another advanced level. So this is the time to see internal energy of a system. Okay, let's try to extend the concept of internal energy of a system to every state of matter. Remember, we have now three states of matter to which this term internal energy should be extended. You can begin with, for example, a liquid. A liquid. We know a liquid, the intermolecular forces are relatively stronger. This is in comparison with a gas because the molecules are relatively closer in comparison with a gas or with a gaseous phase. Therefore, the potential energy contribution to internal energy becomes more significant. Reason the molecules are relatively close to each other. Now, at this point, we shall note that the potential energy contribution of internal energy is as a result of the force between the molecules and the separation between the molecules. As long as the force between the molecules is still significant, for whatever separation, we still have some internal energy. I mean, some potential energy. But of course, for a longer separation, the internal energy may become relatively smaller because even the force becomes relatively weaker. So I am saying as long as there is a force between two molecules or between molecules, then there is potential energy. So potential energy is significant. But of course, as the separation increases, the force becomes smaller. And since the force becomes smaller, then the potential energy contribution also becomes smaller. So we are saying for a liquid, internal energy is still equal to the sum of the kinetic energy plus the potential energy. The kinetic energy component is easy to visualize because the molecules of a liquid are in a continuous random motion. Therefore, they have kinetic energy. But there exists a small force of attraction between the molecules. This force of attraction between the molecules is responsible for the potential energy component, which contributes to the internal energy. We shall see how force contributes to potential energy in a unit called gravitation. We shall see how force contributes to internal energy, potential energy, or how potential energy depends on the force in a unit called gravitation. So, for a liquid, the term internal energy is applicable because for a liquid, the molecules experience a stronger force of attraction compared to the gases, simply because the molecules are close to each other. For that reason, there exists potential energy, or the molecules have potential energy. The molecules are also in continuous random motion, whereby they slide past each other. Therefore, this random motion is responsible for kinetic energy. When I talk about internal energy of a liquid, I'm talking about the kinetic energy of the molecules that make up the liquid due to their random motion, and the potential energy of the molecules that make up the system. Remember, these are distributed randomly. That's why we say it is the sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. That is for the liquid. Let's talk about the solid. Does the term internal energy also apply to a solid? We know that for a solid, the atoms or the molecules are tightly close to each other. In fact, we know that for a solid, the atoms are held tightly together. And we have already established that their motion is restricted to their vibration. Their motion is restricted to vibration about the same point. They do not slide past each other because of the strong intermolecular forces. Because of the strong intermolecular forces, these molecules have potential energy. Because of their vibration about their equilibrium position, these molecules also have kinetic energy. So kinetic energy in solids is due to the vibration of the atoms, and the potential energy contribution is due to the strong binding force. Because the force here is very strong, a layman would really observe that the potential energy here in a solid contributes more. It contributes more than the kinetic energy. In other words, the potential energy contribution is greater than the kinetic energy contribution in a solid. Taking you back to a liquid, because the molecules slide past each other, the force is relatively stronger than that of a gas, but not as strong as that of a solid. In liquids, the kinetic energy contribution could be greater than the potential energy contribution because the force is relatively weaker as compared to the solid. For a solid, the force is extremely stronger. The potential energy contribution could be far greater than the kinetic energy contribution. However, internal energy for a solid is going to be the sum of the kinetic energy and the potential energy of all the molecules which make up this solid. Okay, so that is for the solid. And lastly, for the liquid, for the gas. Now, unfortunately, the gases are going to be classified into two. We have already seen the ideal gas, which is a gas that obeys the equation PV is equal to nRT at all temperatures and pressures. Remember I said the word ideal simply means in practice, such gases do not exist. But we just assume, we make approximations that if in practice we could have a gas existing as a gas at a relatively low pressure, but at a temperature where it is supposed to exist as a liquid, but then it continues existing as a gas. So we call such gases ideal gas. It cannot really exist. So for a real gas, normally every gas we interact with is a real gas. We know that for a real gas, the molecules are relatively far from each other. In fact, they are far, far away from each other. But still, for whatever distance they are from each other, still there exists a small force of attraction or repulsion between these molecules, even though this force is weak. Because this force is weak, it means that the potential energy here is going to be relatively small. For a weak force, which is between the molecules of the gases, the potential energy is going to be relatively small. But remember, the molecules of gas move randomly about each other at a very high speed in any direction. Therefore, they have high kinetic energy. And by the way, these molecules interchange their kinetic energies every time they collide. So, the random distribution of the kinetic energy of these molecules plus the potential energy due to the weak force between the molecules is responsible for the internal energy of a real gas. Now here you will notice, again just like for liquids, you'll again notice that the kinetic energy contribution could be greater than the potential energy contribution. Why? Because the force which is responsible for the potential energy contribution is relatively weaker. Yet the molecules move with high speeds, therefore the kinetic energy contribution to internal energy is relatively high. So for a real gas, the internal energy is going to be the sum of the kinetic and the potential energy of the molecules, where the kinetic energy contribution is relatively far greater than the potential energy contribution. This is for a real gas. For a real gas, internal energy is the sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. But then I want you to remember the ideal gas. What distinguishes the ideal gas from a real gas? Although for real gas the molecules are far from each other, the force is still appreciable, however weak it is. But for an ideal gas, the molecules are considered to be infinitely far from each other. For an ideal gas, the molecules are considered to be infinitely far from each other, so that the intermolecular forces of attraction are completely negligible for an ideal gas. For an ideal gas, the molecules are considered to be infinitely far from each other, so that the intermolecular forces of attraction or repulsion are completely negligible. And if the intermolecular forces of attraction or repulsion are completely negligible, it implies that the potential energy contribution to internal energy boils down to zero. Therefore, for an ideal gas, we are seeing that potential energy therefore becomes zero since the force between the molecules is approximately zero, that is negligible. And if it is negligible, then the potential energy contribution to internal energy is zero. But still, just like the real gas, the molecules move randomly in all directions at a very high speed. Therefore, these molecules have what we call kinetic energy. This therefore implies that it's as if only the kinetic energy will contribute to the internal energy of an ideal gas. It appears as if only the kinetic energy will contribute to the internal energy of an ideal gas. That's why we are saying that for an ideal gas, internal energy is the sum of the potential. That was for real gas. Internal energy was the sum for the potential and the kinetic energies of all the molecules that make up the system. But remember, this is due to the random distribution. Random distribution, because these molecules have a wide range of speeds. They therefore have a wide range of potential and kinetic energies. Therefore, these energies are said to be randomly distributed. Then, for an ideal gas, to compare this with a real gas, we mentioned that for an ideal gas, the intermolecular forces are considered to be negligible because the molecules are considered to be infinitely far from each other. That one particular molecule does not experience a force of either attraction or repulsion from a neighboring molecule. Yet for a real gas, we say the force is there but extremely weak. So the potential energy contribution here is zero. Potential energy contribution is zero for an ideal gas. It means it is only the kinetic energy contribution which is considered for internal energy. Therefore, for an ideal gas, the internal energy of an ideal gas is the same as is the sum of the random distribution of the kinetic energies of all the molecules that make up the system. For an ideal gas, internal energy is going to be the sum of the random distribution of the kinetic energies of all the molecules that make up the system. So we shall not think of the potential energy contribution when we are dealing with an ideal gas, because we have already emphasized that for an ideal gas, the molecules are infinitely far from each other. Therefore, the potential energy contribution to internal energy becomes zero. So it's only the kinetic energy contribution that is considered. So this is for an ideal gas. The sum of all the kinetic energies of all the molecules due to their random motion, or the sum of the random distribution of all the kinetic energy of all the molecules that make up the ideal gas. I have emphasized that the potential energy component does not contribute to internal energy. The reason is because the forces between the molecules are actually negligible. As long as there is no force between the molecules, then there is no potential energy. I think that is home and dry. Okay, so here is a simple conclusion that you should note from what I've been speaking. Note that potential energy of a material depends on two things. Actually, it depends on the separation and the force between the molecules. Many times when the separation is small, the force between the molecules is large. And if the force between the molecules is large, it means the potential energy is also going to be large. The greater the separation, this is actually going to be the smaller the potential energy, not the greater the potential energy. The greater the separation, the smaller the potential energy because the force between the molecules becomes smaller. But later on, when we look at objects which do not have charges, or objects where the force of repulsion is not really going to be experienced, we shall see that again, the greater the separation, the greater the potential energy. Somebody might be wondering how comes that actually when we lift an object from the Earth's surface to a certain height, the gravitational potential energy increases. And the teacher is saying that the greater the separation, the greater the potential energy. Yeah, to you, the gravitational potential energy increases, but you are not knowing that it is actually tending to zero. But the truth is, it is tending to zero. That means elsewhere, the gravitational potential energy is going to be a number which is less than zero. Because at infinity, we shall see that the gravitational potential energy is greatest at infinity and is defined to be zero. We shall see that under gravitation. So as long as the force exists between these two particles, then there is potential energy. If the force ceases to exist due to the separation, then the potential energy contribution becomes zero. That is a simple conclusion from internal energy. So one everyday experience that we normally wish to talk about is why the temperature remains constant, that is during melting or during boiling. Many times you have observed, I think you saw this in IGCS in a unit called thermophysics, that when melting starts, the temperature of ice remains 0 degrees Celsius until all the ice has melted. And when when all the ice has melted, the temperature starts rising. And when the water starts now boiling, again the temperature remains at around 100 degrees Celsius. The question would be, or the question you must have asked yourselves at that point was, where does the thermal energy supplied or the heat supplied go? Now that we know what internal energy is for a system, which is the sum of the kinetic energy and the potential energy of all the molecules that make up the system, so we can now easily explain where the heat supplied goes if it doesn't cause an increase in temperature. So the temperature of a system does not change when there is a change of state. We shall see that in thermophysics later on in a unit called temperature. The temperature of a system does not change when there is a change of state. That one you mentioned in IGCSE. The temperature remains constant whenever there is a change of state. Now the question is, where does the heat supplied go if it doesn't cause a change in temperature? The heat supplied is going to always be used to break the bonds or to separate the molecules by breaking up the bonds between them. So if we are boiling, if we are melting ice, for example, we are turning from solid to liquid. That is actually called diffusion. Turning from solid to liquid. When ice is melting, there is breaking of the bonds so that the molecules which were making up the solid move slightly past each other. So the heat supplied does not actually, the heat supplied will not actually increase the kinetic energy of the molecules, but the heat supplied will go into breaking the bonds between these molecules. The heat supplied will go into breaking the bonds between these molecules. Now here, we are saying that since the heat supply does not cause an increase in temperature because the kinetic energy of the molecules is not changing, then more energy is being supplied or more energy is being used to break the bonds. So that energy is therefore taken in by the system as potential energy. So that energy is going to be converted to the potential energy of the system. So we simply say that the potential energy component increases because we are supplying heat, which is not increasing the kinetic energy of the system, but it is breaking the bonds. So the energy supplied is going to be stored within the system as potential energy as the bonds between the molecules are being broken. So we are saying during melting or during boiling or during a change of state, the heat supplied stops increasing the kinetic energy of the molecules. Instead, it is taken into breaking the bonds. So that energy does not increase the temperature. So the temperature remains constant. But that energy is used into breaking the bonds of the bonds between the molecules. So we say during melting, the kinetic energy of the molecules does not change. It's the potential energy which changes because the bonds are being broken. So that is during melting. And the same applies to boiling. Boiling occurs at around 100 degrees Celsius for pure water. When a liquid starts boiling, then there is a change of state from liquid to vapor or from liquid to gas. And when we had a solid to liquid, the molecules were still close to each other. But then from liquid to gas, the bonds have to be completely broken so that there is completely no interference, or um, there is almost completely no interference of one molecule by another, or there is completely no force between two neighboring molecules, or the force between two neighboring molecules is completely weakened so that the molecules can move freely and randomly in any direction within the liquid. So we shall be seeing this in details under a unit called temperature. So in this part of internal energy, the concept of internal energy is actually going to be helpful to us, because to some people it helps them to distinguish between heat and temperature. At this point, we have seen that for an ideal gas, since the force of attraction between the molecules is negligible, the potential energy contribution was zero. It was only the kinetic energy contribution responsible for the internal energy. So this concept helps us to define what temperature is. And we said, or we are always going to think about temperature as the average. Temperature as the average kinetic energy of the molecules that make up the system. So we shall always look at temperature as the average kinetic energy of the molecules that make up the system. When we say that the temperature has increased, or when you put a thermometer in a liquid and you see a rise in temperature, it's because the average kinetic energy of all the molecules in the liquid has increased. So temperature will be looked at as the average kinetic energy of all the molecules that make up the system. And you will notice that the temperature of a substance does not depend on how many molecules are present in the system. In fact, however fewer molecules present, the temperature does not depend on the number of molecules. However, it will always depend on the average kinetic energy of the molecules present in the system. Note that for an ideal gas, the kinetic energy is going to depend, the total kinetic energy is going to depend on actually how many molecules are there. But the average does not depend on how many molecules are there. Because if I have 10 molecules and I find the average, I could find almost the same average if I had 5 molecules. But what is important is that for temperature, we shall need the average. Yet for internal energy, we wanted the total kinetic energy of the molecules. So you will find that internal energy is going to be affected by the number of molecules which are there. If we have 100 molecules present, then the internal energy is due to that 100 molecules present. So we need the total kinetic energy of all these molecules. That is internal energy. But for temperature, we just need the average. We need the average kinetic energy of these molecules. On the other hand, when we talk about heat or thermal energy, that is just Thermal energy or heat, that is like a form of energy which can be transferred due to temperature differences. I think if there's a difference in temperature between two objects, then heat flows from a region of high temperature to a region of low temperature naturally. That one we know it from IGCSE. Heat naturally flows from a region of Heat naturally flows from a region of high temperature to a region of low temperature. But I mentioned that according to the second law of thermodynamics, heat cannot naturally flow from a region of low temperature to a region of high temperature unless external work is done. And this is exactly what happens with a refrigerator. When you go behind a refrigerator, you'll notice that it's too hot, but that's where again heat is continuously being expelled. The same thing applies to a heat pump or an AC or air conditioner. You will also experience that it is trying to cool a certain place, but behind the air conditioner it is too hot. Simply because heat is flowing from a region of relatively lower temperature, a region of relatively high temperature, but this is not naturally. Some external work is being done. That's why you'll find the AC having a motor. That's why you'll have the AC having a motor. Okay, I think I've said much about internal energy. How can we increase or decrease the internal energy of a system? To begin with, there are several ways of increasing or decreasing internal energy of a system. Number one, remember all we need is to either increase the kinetic energy of the system or increase the potential energy of the molecules that make up the system. So heating, we are going to concentrate on the ideal gas, on the gas in this unit. To increase internal energy, we can apply heat to the gas. If we heat the gas, for example, heating the gas, maybe we have placed the gas in a container. The walls of the container could become hot because we have placed the container on a heat source. It means the molecules of the container vibrate more vigorously. These molecules of the cool gas collide with the molecules of the walls, which are also vibrating, and they will bounce off very fast or more violently. It means the molecules of the gas, when they collide with the walls of the container, they gain more kinetic energy. That's why they bounce off the walls very fast. Since they have gained kinetic energy, remember internal energy is the sum of the kinetic and the potential energy of the system. But now note that we have applied heat and the molecules have gained kinetic energy. So it means the total kinetic energy of the molecules has increased because the molecules, when they collide with the wall, which is hot, whose atoms are vibrating more violently, the molecules of the gas bounce off more violently. That means they have gained kinetic energy. If the total kinetic energy increases, it also means that the average kinetic energy has also increased. And if the average kinetic energy increases, of course, this means temperature has also increased because temperature is the average kinetic energy of the molecules. So already we have seen that the kinetic energy component has increased because we are heating the gas. So we have increased the internal energy because internal energy is the sum of the random distribution of the kinetic and the potential energies of all the molecules that make up the system. Number two, other than heating the gas, we can do work on the gas. Doing work on the gas, think of a balloon where you have blown air or which has been inflated and try to compress the balloon. All of a sudden, you see the balloon bursting simply because you are doing work on the gas or on the air inside the balloon. By doing work or by compressing the balloon, you are doing work on the balloon. Therefore, you are doing work on the gas in the balloon. So if you are compressing the balloon, you are actually pushing the walls of the balloon inwards. So the walls of the balloon are moving inwards. That means a molecule which was moving towards the wall will collide with the moving wall, and therefore it will bounce off faster. That molecule also have gained kinetic energy or more kinetic energy. So that means if many molecules are colliding with a moving wall, the wall is moving inwards, therefore they gain more kinetic energy. Simply it means the total kinetic energy of the molecules has increased. Note that when total kinetic energy of the molecules increases, even the average kinetic energy also increases. And if the average kinetic energy increases, then the temperature has also increased, simply because temperature is the average kinetic energy of the molecules that make up the system. Temperature is the average kinetic energy of the molecules that make up the system. So, we can increase internal energy of a system by heating the gas, that is, heat is added to the system, or by doing work on the system. Work is done on the system, that is by compressing. Okay, on the other hand, we can also decrease. Of course, we can simply do the opposite to decrease the internal energy of a system. We can do the opposite to decrease the internal energy of the system. One, we can leave the system to lose heat. We can allow the system to lose heat, to exchange heat with the surrounding or lose heat to the surrounding. Of course, if it loses heat to the surrounding again, the kinetic energy of the molecules decreases. It also means the average kinetic energy of the molecules decreases, which also implies that the temperature decreases. Remember, temperature is the average kinetic energy of the molecules. We can also allow the system to do work to the surrounding by expanding. When a system expands, or it is a gas, if a gas expands, it does work to the system. It means its molecules are losing energy. They are using up their energy to do work in expanding, that is, in increasing the volume. So, because they are losing energy in doing work with the surrounding, it means the kinetic energy of these molecules reduces. And if the kinetic energy of the molecules reduces, it means the total kinetic energy has reduced. That also implies that the average kinetic energy has reduced, so the temperature reduces. When the total kinetic energy reduces, it means there is a high chance that the internal energy of the system has also reduced. So you might be wondering why when you leave a balloon under sunshine, it simply bursts. It can simply burst because when you leave it under sunshine, number one, the walls of the balloon warm up. The atoms of the balloon vibrate more violently. The molecules inside the gas which is trapped in the balloon collide with the vibrating atoms and bounce off very fast. They have gained enough or high kinetic energy, so they continue bouncing off more violently. As they do, when the internal energy increases inside the balloon, it means the total kinetic energy of the molecules inside the balloon has increased. If the total kinetic energy of the molecules inside the balloon has increased, it also implies that total temperature or the temperature has increased because the average kinetic energy has also increased. Remember, average kinetic energy is the temperature. Average kinetic energy is the temperature. Also note that as they gain more kinetic energy, they bounce off the walls more violently, and therefore the change in momentum increases or the impulse increases. If the change in momentum increases or the impulse increases, the average force exerted on the walls also increases. And since force per unit area is the pressure, it means that the pressure exerted on the walls of the container has increased. All of a sudden, the balloon bursts. So that is the concept of internal energy. At this point, you should now be able to define internal energy. You should now be able to extend the idea of internal energy to the three states of matter. You should now be able to define temperature. You should now be able to distinguish between an ideal gas and a real gas using the concepts of internal energy. That is internal energy. Okay, next we can now talk about the most important part of this, that is thermodynamics, and that is the first law of thermodynamics. In AS, we talked about work, energy, and power. We talked about work, energy, and power. Similarly, in IGCSE, you talked about work, energy, and power. And you recall some of the laws, the conservation laws that we mentioned in AS. One of them was the law of conservation of energy. We mentioned it under work, energy, and power, and we mentioned it under electricity. We said the total energy of the universe is constant, which means energy can neither be created nor destroyed, but could only be transferred from one form to another. Energy can neither be created nor destroyed, but it could simply be transformed from one form to another. So this implied that, or this means that energy cannot simply disappear or appear from nowhere. The concept of conservation of energy will be very important when we talk about electromagnetic induction. Energy can neither be created nor destroyed. It does not appear from nowhere, and it does not just disappear to anywhere. In fact, all the energy we put into, for example, heating the gas to increase its internal energy, or doing work on the gas must somehow end up in the gas. It will not just disappear. We have seen that we can increase the internal energy of the gas by heating the gas or doing work on the gas. So the energy has not been wasted. When we heat the gas, it does not just disappear. The internal energy of the gas increases. When we do work on the gas, the work done does not just disappear. The work done is seen as an increase in internal energy of the gas. So this is actually a law of conservation of energy. But this law could be restated in a similar way in a different way, so that we come up with what we call the first law of thermodynamics. Actually, when I say that the total energy of the universe is constant, or energy can neither be created or destroyed, I'm actually referring to the first law of thermodynamics. But then, if we begin by heating, for example, a gas, the heat we add to the system either does work or changes the internal energy of the system. So it means this law could be restated in a different form, that there must be work done, or thermal energy and internal energy. These three things will always move together. If, for example, we do work on the system, if, for example, we add heat to the system, where does the heat go? If I have a system of a gas which has been enclosed somewhere here, the law of conservation of energy is telling me that if I apply heat Q here to the system, this heat must end up into the gas. It has two things that it can do. One, it can change the internal energy of the gas, and two, it may make the gas to push the walls of the container, that is to do work onto the system. So there are three things here: heat applied, change in internal energy, and some work done. So the arrows could point in different directions. For example, the system can lose heat, or work can be done onto the system, and the system's internal energy could increase, and so on and so forth. So if we try to restate the first law of the first law of, the law of conservation of energy, we would be thinking about this, that all the energy we supply to the system does not just disappear. It may end up as internal energy and also do work. It may end up as internal energy of the system, or it may change the internal energy of the system by either increasing it or decreasing it, or work might be done either on the system or by the system. So we can therefore simply say that a change in internal energy of the system can be given as the energy supplied by heating plus the energy supplied by doing work. This is the first law of thermodynamics. The change in internal energy of a system is equal to the energy supplied by the system plus the energy supplied by doing work. Somebody might be wondering, what do we mean by thermodynamics? I think thermo relates to heat, and dynamics means relates to changing, like normally when we are growing up, our targets in life are dynamic. They keep changing. The things we love keep changing. The people we meet keep changing. The society keeps changing. Everything is dynamic. So when we talk about thermodynamics, in thermodynamic, we study processes involving transfer of thermal energy and doing work. The term thermodynamics is the study of processes involving transfer of heat energy or thermal energy and doing work. That's what we mean by thermodynamics. We study processes involving transfer of thermal energy and doing work. So we are saying that the amount of the change in internal energy could depend on the heat supplied by heating and the energy supplied by doing work. Here I just considered one side or one direction, because if heat is supplied by heating, it means heat is added to the system. This increases the internal energy. If energy is supplied by doing work, it means work is done on the system. This also increases the internal energy. So it means this change of internal energy is most likely going to be an increase. But it is also possible that the change is a decrease. It is also possible that the change is a decrease, as we are going to see. But for now, the change in internal energy is going to be given as, I will simply write this as delta U to mean change in internal energy is given by heat supplied by heating Q plus energy supplied by doing work, which is going to be a small letter W. Many times you'll find the first law of thermodynamics just written like that. Remember, the work done by a gas is given by pressure times the change in volume. We saw this in AS. The work done by the gas or on the gas is given by pressure times change in volume. If work is done on the gas, it means delta V is decreasing. The volume is not delta V. The volume is, this means the volume is decreasing. If the work is done on the gas, this is a compression. On the gas, that is a compression. It means the volume is decreasing. If the work is done by the gas, it means the volume is increasing, and this is an expansion. It is very important to note whether the work is done on the gas or by the gas, because we know that when work is done on the gas, energy is added to the system. Most likely the internal energy increases. But if work is done by the gas, it is the gas doing work to the surrounding. It is using up its energy to do work, to increase the volume. So it means the energy within the system is actually reducing. So you must note this very well. So it means the change in internal energy can sometimes be written as Q plus, I will say plus or minus, P delta V, where delta V is change in volume. But most likely you'll always write it as simply that. Now in thermodynamics, it is going to be very important for us to define a system which we are considering. Because if we don't define the system being considered, then we shall not know whether the work is done on the system or by the system. We shall not be able to identify whether heat is added to the system or is released by the system. We shall not be able to tell whether the internal energy is increasing or decreasing. So we must always define the system. Take for example, let us think of a system which is an ideal gas. We are going to think of a system which is an ideal gas trapped in a piston. Trapped by a piston in a frictionless cylinder. So we have an ideal gas which has been trapped. Here we have a gas that has been trapped by a piston in a frictionless cylinder, as you can see. So this my system here is an ideal gas. So I have defined my system as an ideal gas. Then the ideal gas is trapped by a piston which has been fitted inside a frictionless cylinder. So now I can think of several other conditions, whether heat is added to the system or heat is done by the system. So if the gas expands, it means it pushes the piston. The volume is increasing. So work is done by the system. The system is using the already existing energy to push the piston. So if the gas expands and pushes the piston, already the existing energy is being wasted in pushing the piston. This means most likely the internal energy is going to reduce because the work is done by the system. I want you to recall that work is done when energy is transferred, most likely by mechanical means. And we have just seen that heating is a transfer of energy, especially due to a difference in temperature. So it means work and heating both involve a transfer of energy, but in different ways. For work, energy is transferred by mechanical means. For example, here the gas expands and pushes the piston. The gas is transferring energy to the piston by mechanical means, by movement. Yet, another way of transferring energy could be applying heat direct. Here, energy flows from a region of high temperature to a region of lower temperature naturally. We have also seen that internal energy of a system is actually the sum of the random distribution of the kinetic and the potential energies of the molecules that make up the system. Now recall, my system, which I have defined is an ideal gas. I've defined my system as an ideal gas, and remember, for an ideal gas, potential energy of the molecules is approximately zero because the molecules are infinitely far from each other. That means the intermolecular force is negligible. But the molecules have kinetic energy. The kinetic energy contribution, it is the kinetic energy responsible for the internal energy. So since this is an ideal gas, the internal energy of an ideal gas is going to be only equal to the total kinetic energy of the molecules. Or the internal energy of an ideal gas is only going to be equal to the total kinetic energy of the molecules which make up the ideal gas. Now here, I expect that the internal energy of the ideal gas is going to increase if I add heat to the surrounding. If I add heat to the surrounding, I expect that the internal energy should increase because the molecules would gain more kinetic energy. Or if I push the piston inwards, I would be doing work with the ideal gas. I also expect that the internal energy will increase because the kinetic energy of the molecules will also be increasing. So in both cases, whether we are heating the gas or whether we are compressing the gas, we are adding energy to the system. And by conservation of energy, this energy cannot just disappear. It must be transformed to another form or another type of energy. Therefore, the energy which is the work done in pushing the piston will appear as a change in internal energy of the gas. The energy we apply by heating will end up as an increase in internal energy of the gas. So it appears as an increase in the internal energy of the gas. That is to say, the total kinetic energy of the molecules of the ideal gas will be increased. Because I want you to note, for an ideal gas, the potential energy contribution is zero. It's only the kinetic energy contribution which is important. Because we are compressing the gas or we are applying heat to the gas, the kinetic energy of the molecules increases. That means the total kinetic energy of the molecules has increased, which means that the internal energy of the gas has increased. But remember also, if the total kinetic energy of the molecules increases, it means that the average kinetic energy of the molecules has also increased. Remember, temperature is the average kinetic energy of these molecules. Note very well, the energy we have supplied by either doing work or heating has increased the internal energy, which means the total kinetic energy of the molecules has increased. This implies that the average kinetic energy of the molecules has increased, which therefore implies that the temperature of the system has increased. So, increase in temperature means an increase in the average kinetic energy, which means an increase in the total kinetic energy, which means an increase in internal energy. Moving backwards, an increase in internal energy means an increase in the total kinetic energy of the molecules, which means an increase in average kinetic energy of molecules, which means an increase in temperature. Therefore, addition of energy to my ideal gas will imply or will show up or will appear as an increase in the temperature of the ideal gas. The reverse is very true. If the gas pushes the piston, it will be losing its energy. Therefore, its internal energy decreases. The total kinetic energy of the molecules decreases. That means the average kinetic energy of the molecules decreases. Therefore, the temperature also decreases. I hope I've tried my level best to explain this part because it is the most important part. It is actually the most important. Okay, so in summary, let's have a simple summary, I guess. In summary, the first law of thermodynamics can simply be given as the change in internal energy is equal to Q plus W, where delta U is change in internal energy. Now Q, we shall not say heat supplied to the system, but that's just thermal energy. Thermal energy, and the W is work done. I don't want to say for now that W is work done on the system, because the system can also expand and work can be done by the system. I don't want to say thermal energy added to the system, because the system can give out energy, so thermal energy can be released by the system. This takes us to what we call the adapted sign conventions. In dealing with all these, we need what we call sign conventions. We shall need what we call sign conventions. Remember, the equation is change in internal energy. The change in internal energy is equal to the amount of heat plus work done. This is the first law of thermodynamics. Now, the change in the sign convention, at some point, Q will be added to the system or the system loses heat. That means Q should either be positive or negative. At some point, the system does work or work is done on the system. Therefore, W at some point should either be positive or negative. At some point, delta U, the internal energy increases or the internal energy decreases. So at some point, delta U should either be a positive or a negative to show an increase or a decrease. So what is this sign convention? Number one, if we have a positive Q in calculation, the positive Q or positive value of heat supplied, this will be heat added to the system. Thermal energy added to the system will be assigned a positive value. If they say 20 joules are used to heat the gas, because it is added to the gas, this will be positive. Number two, a positive value of W also means that work is done on the system. If we say the gas is compressed by 20 joules, it means this will be positive. This is added to the system. Number three, a positive value of delta U also means an increase in internal energy. So when I see a positive value of delta U, it will mean that there has been an increase in internal energy. Number 4, if I see a negative value of delta U, it means that is a decrease in internal energy. Decrease in internal energy is going to be a negative value. In calculation, you calculate change in internal energy and you get a negative. The negative indicates a decrease. The question will be state the direction of the change in internal energy. Here you can't say west, east, south, and so on. The direction will be a decrease. They state the change in internal energy and you have calculated that it is positive, so the direction will be an increase. So you must note that in calculation. Number 5. Number 5. If I get a negative, if I have a negative value of Q, if I was told that the system loses heat to the surrounding, that means the negative value of Q means the heat leaves the system, or thermal energy is released or given out by the system. That is a negative value of Q. Of course, a negative value of Q means the internal energy of the system reduces. And lastly, a negative value of W. A negative value of W means the work is done by the system. That is especially when the system expands. So if I say the system expands, it means the work done by the system must be assigned a negative value. If I'm told that the system expands, it means the system is doing work to the surrounding. And when work is done by the system, the work done is assigned a negative value. This is a sign convention. A convention is a rule. So there are no questions there. Convention is a rule. We shall borrow this rule for calculations. So, having known this sign convention, before we see calculations, let's see a few applications of the first law of thermodynamics. Number 1, an adiabatic process. Let's consider a change in the volume and the pressure of a gas which is trapped in a cylinder by a frictionless piston. So we have a gas that has been trapped by a piston in a cylinder. So let us assume that the cylinder has been perfectly insulated. For this insulation, it means no heat enters or leaves the system. That means the amount of heat added or leaving the system is going to be zero. This is going to be called an adiabatic process. A thermodynamic process which occurs with no thermal energy allowed into or allowed to leave the system. No thermal energy, no heat enters or leaves the system. Such a process which occurs with no heat entering or leaving the system is said to be an adiabatic process. Let's use the first law of thermodynamics to see what happens with the adiabatic process. Since my cylinder has been perfectly insulated and it is trapping a gas in here, the value of Q is zero. No heat enters or leaves the system. The first law of thermodynamics states that the change in internal energy is equal to Q plus W. But now this is zero. So it means the change in internal energy is going to be simply equal to the work done. What does this imply? That the change in internal energy is equivalent to the work done. Now here, it will depend on what is happening. Let's think of work being done on the gas by pushing the piston. Let's now push the piston inwards. Remember, work done is equal to pressure times the change in volume. Because the piston is moved inwards, the volume is decreasing, work is done on the gas. That is a compression. When work is done on the system, the work done is assigned a positive value. If I assign work done to be positive, automatically the change in internal energy will be positive. Since work done is positive, the change in internal energy is going to be positive. Therefore, work being done on the system causes an increase in internal energy of the system. It makes sense when you compress a balloon and then it ends up bursting. The internal energy inwards, inside the balloon, was increasing, meaning the total kinetic energy of the molecules inside the balloon was increasing, meaning the average kinetic energy of the molecules inside the balloon was increasing, which means the temperature inside the balloon was increasing. So I am saying if work is done on this piston, for example, by pushing it inwards, W will be positive because we have said by the sign convention, work done on the system is positive. And if this is positive, the change in internal energy is also going to be positive because the amount of heat supplied for an adiabatic process is zero since this is a perfectly insulated system. The internal energy increases, which means the total kinetic energy increases, so internal energy has increased, which implies that the total kinetic energy has also increased, which implies that the average kinetic energy has also increased, which implies that the temperature must have increased. A very simple analysis. A very simple analysis. But we can have, by the way, without even doing work with the system, or without even insulating. We may not even insulate, but we can continue doing work. We may not insulate. An adiabatic change or an adiabatic process can still be achieved by moving the piston rapidly. If you have had a bicycle and you try to pump air into the bicycle very fast, that is called brisk pumping. You try to pump air into a bicycle, into the tube of a bicycle, and you pump very fast, very rapidly. In a very short time, when you remove the pump and you touch you remove the valve, you will notice that the air inside is warm. The air coming out of the tube is going to be warm because you have been pumping very rapidly, but you have not applied any heat. But because of the rapid pumping, the rapid pumping or the brisk pumping, you didn't allow the gas to lose its thermal energy to the surrounding. So it means the thermal energy went on accumulating. Even though there was no insulation, an adiabatic process has occurred. In fact, in thermodynamics, we would call it an adiabatic compression. So, work is being done on the gas as we pump rapidly, but no heat is lost or there is no time for heat being lost, yet work is being done. And the internal energy therefore increases, which means that the temperature also increases. But of course, you know that when you leave the bicycle tube somewhere in a room for some time, and again you open the valve, you will be shocked that now the air coming out. Remember, initially when you had just finished pumping, the air coming out was warm. But after some time, you'll notice that the air coming out is cooler than the surrounding. Those are actually some of the most abstract concepts of thermodynamics, which I don't want to go into. Let's define another system. It can be an electric kettle containing water. So think of an electric kettle containing water. This time, because it is an electric kettle, heat is going to be added to the system. So Q is not zero. But the quantity Q, because of the sign convention, the quantity Q will be positive. But to an initial approximation, before the kettle expands, because of course when you are heating the kettle, I think it is also going to slightly expand. But before the kettle expands, some kettles do not actually expand much. When you are heating, the heating element is at the center of the kettle. Sometimes the kettles may not even expand much. So if we define another system as such as an electric kettle, then in this case, the change in internal energy, which is given by Q plus W, because the kettle will not expand much, the work done is going to be zero. Because remember, work done is going to be pressure times change in volume. The pressure is constant, the volume does not change much. Therefore, the work done is approximately zero. And if that is zero, it means the change in internal energy is only depending on the heat supplied. If you are adding heat to this, if the heating element is switched on, then delta Q is going to be positive. And if delta Q is positive, then delta U is also positive. A positive value of delta U implies an increase in internal energy. So here we have defined another system, which is an electric kettle containing water. The heating element provides heat. That's why Q is positive. Heat is added to the system. We are saying if the kettle does not expand, it means there is no work done. Of course, we don't expect it to be compressed. So that gives us another system. So every time we use the first law of thermodynamics, we shall also be defining the system. We shall be defining the system. There are important points for us to note. Number one, when a substance changes from a solid to liquid, for those of you who know physics, this is called fusion. Change of state. What happens? It is the intermolecular bonds which are being broken. And we said when these bonds are broken, the potential energy component of the internal energy increases. But the kinetic energy component does not change. That's why when a solid changes to a liquid, when ice starts melting, the temperature remains 0 degrees Celsius until all the ice has melted. During the melting process, the temperature does not change. Therefore, the kinetic energy of the molecules does not change. Most substances, of course, expand on melting. That means external work is done. Some external work is done. But this would imply that by the first law, thermal energy must be supplied to the system. And this thermal energy is what we are going to call the latent heat. So if ice melts, we expect it to slightly expand. And if it slightly expands, it would imply that thermal energy, internal energy is supposed to decrease. But we are continuously supplying the heat. That means that heat is going into doing external work. That heat is increasing the potential energy component. It is doing the external work by causing an expansion, but it is not changing the kinetic energy of the molecules. Therefore, we don't see physically the effect of this heat. That's why we call it latent. We don't see physically the effect of the heat supplied. That's why we call it latent heat. But we are sure that this heat must be going somewhere. It must be doing something. And to be specific, it does external work. It causes an expansion because when some substances expand, undergo change of state, such as solid to liquid, they tend to expand. So work must be done in breaking the bonds. And that heat supplied is called latent heat. The word latent means concealed. We don't physically see the effect. Because if we had a thermometer in the liquid, we would notice that during melting, the reading of the thermometer would remain 0. Then we would remain with the question, where is the heat going? This heat just goes into breaking the bonds, doing external work, because if the bonds are being broken, the volume increases. I think that is interestingly clear. So during the melting process, the temperature does not change. Therefore, the kinetic energy of the molecules does not change. That's what happens during melting. But I said most substances expand on melting. That means external work is done when the substance melts. And by the first law, thermal energy must be supplied to the system. And this thermal energy is the latent heat. Because the first law states that change in internal energy is equal to Q plus work done. So change in internal energy is equal to Q plus pressure times change in volume. So when a substance melts, it tends to expand, meaning that the volume is increasing. If the volume increases, that means work is done by the system. It means the work done by the system would cause a decrease in internal energy, but this is compensated for by adding heat. So heat is added to the what? To the system. So this heat which is added to the system compensate for the work done by the system is what we are going to call the latent heat. This does not cause a change in temperature, but it can cause an increase in internal energy. Okay, and lastly, the volume changes associated with evaporation are much greater than those associated with melting. I always don't like using the word evaporation. I prefer using boiling, but this time I'll use vaporization or evaporation. I'll use vaporization, not evaporation. The spelling of vaporization. Where do you expect a lot of heat to be required? Is it when a substance is melting or when a substance is undergoing vaporization? We have said because some substances expand when there is a change of state, heat is supplied to compensate for that expansion. This heat is the one which goes into breaking the bonds. Otherwise, the internal energy would decrease. And that heat, we have called it latent heat. It is either going to be called latent heat of vaporization or latent heat of fusion. Latent heat of vaporization or latent heat of fusion. So in all cases, either during melting or during vaporization, there is a change in volume. In fact, there is an increase in volume. However, the increase in volume associated with melting is smaller than the increase in volume associated with evaporation or vaporization. What is the implication of this? The latent heat of vaporization is always going to be much greater than the latent heat of fusion. The latent heat of vaporization is always going to be much greater than the latent heat of fusion. The reasons are very simple. During vaporization, there is a greater change in separation of the molecules. That means there is a greater increase in potential energy, and therefore there will be a greater increase in internal energy. During vaporization, a lot of work is done to push against the atmosphere as molecules escape from the liquid phase to the vapor phase. So the volume change involved during vaporization is far greater than the volume change involved during melting. The change in volume when ice melts to a liquid is far, far smaller than the change in volume when a liquid or liquid water changes to vapor. And remember, the change in internal energy is equal to Q plus work done. And the change in internal energy is equal to Q plus pressure times change in volume. The change in volume due to vaporization is far, far larger than the change in volume due to melting. That means a lot of heat is required during vaporization as compared to that heat required during melting. That's why we are going to say that the latent heat of vaporization is much greater than the latent heat of fusion, because the volume change involved during vaporization is far, far much greater than the volume change involved during melting. In fact, we are saying there is a greater change in volume as the gas molecules push back the atmosphere because they are trying to escape the atmosphere. So they tend to push back, they push against the atmosphere. So more work is done during vaporization than during melting. Since more work is done during vaporization, more energy or more heat is used during vaporization than during melting. That's why we say that the latent heat of vaporization is much greater than the latent heat of fusion. Note that latent heat of vaporization is that amount of heat required to change a liquid to a solid at constant temperature. The amount of heat required to change a liquid to a solid at constant temperature is what we call the latent heat of vaporization. We shall see this in details in the next unit. And the amount of heat required to change a solid to a liquid at constant temperature is what we call the latent heat of fusion. So remember, the word latent means the heat is concealed. And because it's concealed, we don't see the physical effect. That's why we are emphasizing that the temperature remains constant. There is a change of state at constant temperature. The amount of heat required to change a state without changing temperature, or to change the state of a substance without changing temperature, is what we are going to call the latent heat. The amount of heat required to change the state of a substance without changing temperature is what we are going to call the latent heat. And if we are changing from solid to liquid, we shall call it the latent heat of fusion. If we are changing from liquid to vapor or liquid to gaseous, we are going to call it the latent heat of vaporization. In all cases, the system expands, external work is done. To compensate for the energy wasted in doing work or in breaking the bonds, heat is supplied. That heat is what we call the latent heat. Okay, I think that is almost the end of this unit. We just need to do a few examples. We now have to qualify for examples. I think I've explained this, why latent heat of vaporization is greater than latent heat of fusion. I've said when evaporating, greater change in separation of atoms or molecules occurs. This would give an increase in potential energy and thus an increased internal energy. And the most important one is this part here. There's a greater change in volume. A greater change in volume occurs as the gas molecules push back the atmosphere. Thus, external work done is much greater. This is during the latent heat of vaporization, or during change from liquid to solid. I mean liquid to gas, not liquid to solid. Okay. Examples. I think we can run through the examples. The examples here are quite very easy. I don't know why they are quite very easy, but we shall see the real examples in past paper questions. These ones are just for now. Example number 1. We have 200 joules of thermal energy added to the system. 200 joules of thermal energy added to the system. So very first I will say Q is equal to positive because thermal energy is added. So this will be positive 200 joules. Find the change in internal energy of the system. They said which does work. It means that it is the system which is doing work. Because the system is doing work, according to the sign convention, work done by the system is negative. So I'll put here a negative. So this will be negative 1,150 joules. Find the change in internal energy of the system. So we have already seen that the change in internal energy is equal to Q plus W according to the first law of thermodynamics. So this will be equal to Q, which is now positive 200, plus W, which is negative 150. And when you press your calculator, even without pressing the calculator, this is positive 50 joules. You notice that this change is positive. And because it is positive, the direction of the change in internal energy is an increase. A positive change in internal energy means an increase in internal energy. A positive change in internal energy means an increase in internal energy. Okay, next, example number 2, without wasting time. An isothermal change is one which takes place at constant temperature. The word iso means the same, thermal, now this is relating to heat. So isothermal, that is a change which takes place at constant temperature. Explain why in any isothermal change, the change in internal energy is zero. In such a change, 200 joules of thermal energy is added to the system. How much work is done on or by the system? We don't know whether it is on or by the system. So let's begin. By the first law of thermodynamics, change in internal energy is equal to Q plus W. This is an isothermal change. This is an isothermal change. Explain why in any isothermal change, the change in internal energy is zero. For an isothermal change, in one of the lessons, I must have said that if the initial temperature is the same as the final temperature, then the change in internal energy is zero. The kinetic energy, the total kinetic energy of the molecules initially is the same as total kinetic energy of the molecules afterwards. That means the average kinetic energy of the molecules initially is the same as the average kinetic energy of the molecules afterwards. And if the total kinetic energy of the molecules initially is the same as total kinetic energy afterwards, then the total internal energy, the change in internal energy of this system will be zero, because the initial internal energy of the system is the same as the final internal energy of the system. Remember, if our system is an ideal gas, the internal energy of the ideal gas is the sum of the random distribution of the kinetic energies of all the molecules that make up the system. The total kinetic energy of the molecules is the internal energy. The average kinetic energy of the molecules is the temperature. And if the initial temperature is the same as the final temperature, remember, isothermal means constant temperature. If the initial temperature is the same as the final temperature, then total kinetic energy initially is the same as total kinetic energy afterwards, so the change in internal energy is zero. So the reason as to why for an isothermal change, the change in internal energy is zero, we have seen the initial temperature is the same as the final temperature, and if that is true, the change in internal energy is going to be, there is no change in internal energy. Okay, let's go back to the calculation. In such a change, 200 joules of thermal energy is added, so that means Q is positive, 200, because it is added. How much work is done on or by the system? We have already seen that delta U is 0, so I will say 0 is equal to positive 200 plus W. Making W the subject, you notice that W is now going to be equal to negative 200 joules. Do we notice that W is now a negative? And if W is a negative, by the sign convention, negative W means work is done by the system. In other words, the system could be expanding. So, to be specific, work is done by the system because the system is expanding. The negative is indicating work is done by the system. Okay, I hope that is fine. Number 3. The first law of thermodynamics may be expressed in that form. Explain the symbols in this expression. This is an increase in internal energy. Increase in internal energy. This is heat added to thermal energy added to the system. This is work done on the system. This is a decrease. Negative is a decrease in internal energy. Negative Q is heat released or given out by the system, and negative W is work done by the system. That is the sign conversion, and you should make it a part of you if you want to always pass these questions. Number 4. A gas is heated by supplying it with 250 kilojoules of thermal energy. So very fast, you notice that Q is positive, 250 kilojoules, because it is added to the system. At the same time, it is compressed. So work is done on the gas. So W is also going to be positive, plus 500 kilojoules. It is compressed. Calculate the change in internal energy. So change in internal energy is equal to Q plus W. Since both are positive, I'll just say positive 250 plus positive 500, which will give me 750 positive, that is kilojoules. The positive is indicating an increase in internal energy. Whenever we calculate delta U and it is positive, so this is an increase. The direction of the internal energy is an increase. So it is an increase in internal energy. Okay, so that was part A. I don't know whether there is part B. Some gas is heated as before with the 250 kilojoules of energy. This time the gas is allowed to expand so that 200 kilojoules of work on it, so that it does 200 joules of work on its surrounding. So some gas is heated as before with that. So Q is positive. Q is going to be positive 250 kilojoules because heat is added to the gas. This time the gas is allowed to expand. So since it expands, the work done is negative 200 kilojoules. Calculate the change in internal energy. So the change in internal energy this time is going to be Q plus W. So this is positive, Q is positive 250, but W is negative 200. When you sum up, this gives you positive 50 kilojoules. It is still positive, so still this means an increase. That is an increase in internal energy. That is still an increase in internal energy. Okay, next, number 5. In number 5, we have a diagram which is we are moving from say P to Q. When the gas is taken from state P to R by the stages PQ and QR, 8 joules of heat are absorbed by it. So when we follow this PQ, QR, 8 joules are absorbed. So this is going to be positive because it is absorbed. No, 8 joules is positive, is absorbed. So it is added to the system. And 3 joules of work are done by, so this will be negative because it is done by the system. For stage PS and SR, 1 joule of work is done by the gas. Determine if heat is released or absorbed and the amount. So let's think of PQ to QR. We are moving from P to R but following the stage PQ to QR. So we are using the first law of thermodynamics. The change in internal energy is equal to Q plus W. So the change in internal energy is going to be equal to, this is positive because it is absorbed, so that is positive 8, plus this will be negative because it is done by, so this will be negative 3. And when you get the change in internal energy is equal to, this is going to be positive 5 joules. So that is the change in internal energy. So whether I follow PQR or I follow PSR, the change in internal energy is the same because we just need the difference in internal energy between P and Q. So it means if I now consider another path, so I'm now going to consider PS to SR. PS to SR, the change in internal energy should remain the same. Change in internal energy is going to be equal to Q plus W. So I want to see whether it is an increase, I mean heat is added to the system or is released by the system. So this will be positive 5 will be equal to Q plus. For stage PS and SR, 1 joule of work is done by the gas. So this is going to be negative because it's done by the gas. So that will be minus. And when I try to make Q the subject in this stage, Q will be equal to 5. This is minus 1. So Q will be 5 plus 1, which is equal to 6 joules. So when I follow PSSR, Q is going to be 6 joules and it is positive. The positive value of Q means the heat is absorbed. So we conclude that it is absorbed or added to the system. Okay, so that is example number 5. Number 6. Example number 6, and perhaps it could be one of the last. A fixed mass of an ideal gas undergoes a cycle PQRP. PQRP. We are coming back to the same point. PQRP. That means if I started from point P using this pressure and this volume, the temperature here will always be the same. That means if I come back to point P, I'm coming back to the same temperature. At P, the initial temperature and the final temperature are the same. So the question here is saying, state the change in internal energy of the gas during one complete cycle. Whenever we have one complete cycle, the initial temperature is the same as the final temperature. So the change in internal energy is obviously zero. If the initial temperature is the same as the final temperature or for an isothermal process, I want to emphasize that the change in internal energy is always zero. For an isothermal temperature, the change in for an isothermal process, the change in internal energy is always going to be zero because the initial temperature is the same as the final temperature. If we come back to the same point, we are coming back to the same temperature. Temperature is the average kinetic energy of the molecules that make up the system. If the average kinetic energy of the molecules is the same, it means the total kinetic energy of the molecules has remained the same. And remember, for an ideal gas, internal energy is the total kinetic energy of these molecules. Therefore, if we come back to point P, the total change in internal energy will be zero. So if arrows are like this, coming back to the same point where we started, always remember that total change in internal energy is zero. It doesn't mean that the change from R to P is zero. Neither does it mean that the change from Q to R is zero. But the total, when I come back to point P, the net change becomes zero. Calculate the work done on the gas during the change from P to Q. Note that from P to Q, the pressure is the same. So this is going to be called an isobaric process. Isobaric constant pressure. Work done by a gas is equal to pressure times change in volume. This will be equal to pressure, which is 4 times 10 power 5. Change in volume, we are moving from 8 to 2. So that is 8 minus 2, then times 10 power negative 4. And when you press your calculator, you most likely get so when I press my calculator, I'm getting 240 joules as the work done on the gas during the change from P to Q. You can even see that work is done on the gas because the volume is decreasing. It is a compression. Work is done on the gas from P to Q because it is a compression. Next, some energy changes during the cycle PQR are shown. Complete the table. They have showed us that from Q to R, I can sketch here my graph so that I can easily use it easily. So we have from P to Q to R, like that. So they are saying from Q to R it is 0. That is obvious because the volume is remaining 2. This was 8. This was 4. I don't know what that is. So from Q to R, that is obviously 0. And if that is 0, remember this is W, this is Q. So it means this, if this is 0 and this is plus 720, the change in internal energy is always going to be Q plus W. So this should be plus 720. That is obvious. This one from P to R, P to Q, we have calculated it in the previous question as 240, and it was positive because work is done on. So this will be plus 240. Using this formula here, we have 240 plus negative 600 should give us the change in internal energy. 240 plus 600 negative. So this is going to give us negative 360. That's negative 360. But remember, when we come back to point P, the total change in internal energy should be 0. So when I move from P to Q, which is negatives, the change in internal energy is that. From Q to R, which is the change in internal energy is that. Then from R to P, the total should be 0. Total change in internal energy should be 0. So if I call this one X, so I'll say that X plus 720 plus negative 360, the total of all these will be 0. So that means when you press this, X will be equal to negative 360, I guess. Is it negative 360? Total change should be 0, so this will be 720 minus 360. Yeah. So X is going to be negative 360 joules. So I can now move backwards. I now want here using the same equation, first law of thermodynamics. When I add this, change in internal energy is negative 360 should be equal to Q, which is plus 480. Then plus this value here, let me call this one W. So plus W. So if I want to find W, so that will be negative 360 minus negative 360 minus 480, which gives us our value of W as negative 840. So here we have negative 840 joules. So that is our table. So I have just been playing around with the first law of thermodynamics, and I have been able to come up with this to fill this table, and I think that marks the end of this unit. But of course, before we go, you are going to attempt the following assignment. Number 1, state the second law of thermodynamics. Number 2, distinguish between a real gas and an ideal gas. Number 3, define temperature using the kinetic theory of matter. Define temperature using the kinetic theory of matter. Number 4, explain what you understand by the term thermodynamics. Explain what you understand by the term thermodynamics. Number 5, explain what is meant by latent heat and distinguish between latent heat of fusion and latent heat of vaporization. I said, explain what you understand by the term latent heat and distinguish between latent heat of fusion and latent heat of vaporization. And lastly, explain why the latent heat of fusion is far, far smaller than the latent heat of vaporization. I hope that was an interesting lesson, and I hope to stop here for now. Have a good day. Attempt the exercise and submit as usual. Bye bye.